The universe is 13.8 billion years old. The Milky Way alone contains somewhere between 100 and 400 billion stars. And yet, silence. No signals. No visitors. No evidence whatsoever that any intelligence other than our own has ever existed anywhere in the cosmos. Either we are the single most improbable accident in the history of existence, or something is wrong with everything we think we know. John von Neumann understood this before anyone else had the courage to say it out loud. He was the man who helped build the atomic bomb, laid the mathematical foundation of quantum mechanics, and invented the architecture that every computer on Earth still runs on today. When a mind like that turns its attention to the question of extraterrestrial life, it does not speculate. It calculates. And what he calculated should terrify you. Von Neumann proved mathematically that a single self-replicating machine, launched just once, from just one civilization, could colonize the entire Milky Way galaxy within a few million years. Not billions, not hundreds of millions, a few million. In cosmic time, that is not even a rounding error. That is a Tuesday afternoon. Given that civilizations far older than ours almost certainly had the time, the intelligence and the resources to build such a machine, they should have. And if they did, those machines should already be here, around this star, on this planet, watching us right now. But they are not. Or at least, that is what we have been told to assume. This is not a fringe thought experiment buried in a physics journal. This is one of the most destabilizing unsolved problems in all of science, and the mainstream refuses to look directly at it, because the answers it points toward are deeply, profoundly uncomfortable. Either intelligence is almost impossibly rare, rarer than we can emotionally accept, or something systematically destroys civilizations before they reach this capability, or the machines are already here and we have simply failed to recognize them, or our entire model of how intelligence spreads through the universe is catastrophically wrong. Every answer is a crisis. There is no comfortable exit from this problem. Von Neumann handed humanity a locked room mystery. He sealed it shut with mathematics, and then had the audacity to die before telling anyone which door leads out. What follows is what he left behind, and what it actually means. To understand why this problem is so serious, you have to understand who John von Neumann actually was. Not just his titles or his awards. You have to understand how his mind worked. Von Neumann was born in Budapest in 1903. By the age of 6, he could memorize entire phone books. By 8, he was working through university-level mathematics on his own. His teachers ran out of things to teach him before he was a teenager. The mathematicians who later worked alongside him at Princeton did not describe him as gifted. They described him as something different, something that did not fit neatly into any category they had for human intelligence. He did not just solve problems, he dissolved them. He would hear a problem for the first time and produce a solution before most people had finished writing the question down. He worked across physics, economics, biology, and computer science simultaneously, and made foundational contributions to all of them. He was not a specialist. He was something closer to a force of nature wearing a suit. And in the late 1940s, while most scientists were still focused on the immediate aftermath of World War II, von Neumann turned his attention to a question that seemed almost abstract at the time. He asked, is it theoretically possible to build a machine that can copy itself? This sounds simple. It is not simple at all. Think about what self-replication actually requires. A machine that copies itself needs to be able to gather raw materials. It needs to process those materials into components. It needs to assemble those components correctly. It needs to store the instructions for doing all of that. And it needs to pass those instructions on to the copy it just made. Every single one of those steps is a massive engineering challenge, and von Neumann wanted to know if all of them together could be done by a machine operating without any human help. He concluded that yes, they could. Not only could a self-replicating machine be built in theory, he worked out the exact logical structure such a machine would need. He described it in mathematical detail decades before anyone had the technology to attempt it. What he described maps almost perfectly onto the structure of biological DNA. He worked this out before the double helix was even discovered. That is the level we are dealing with here. But von Neumann did not stop at biology. He kept going. He asked the next question. If a machine can copy itself once, what happens when you let it run? The answer is exponential growth. One machine becomes 2. 2 become 4. 4 becomes 16. 16 become 256. The numbers do not grow steadily, they explode. And in space, where there is no shortage of raw materials, asteroids, moons, dead planets full of iron and carbon and silicon, a self-replicating machine would have everything it needs to keep doubling, indefinitely, across the entire galaxy. Von Neumann calculated that a probe launched from Earth today, traveling at just a fraction of the speed of light, could reach the nearest star in roughly 1,000 years. Once there, it mines the local asteroids, builds copies of itself, and sends those copies to the next nearest stars. Each of those copies does the same thing. Within a few million years, every star system in the Milky Way has been reached. Every corner of the galaxy has been touched. The entire project, from launch to completion, takes less time than the gap between us and the dinosaurs. Let that land for a moment. Any civilization that existed 2 million years before us, which in a 13.8 billion-year-old universe is not a long time at all, would have had enough of a head start to fill the entire galaxy with their machines by now. Not just to reach our solar system, to thoroughly, completely, saturate every corner of the Milky Way. To be so present throughout the galaxy that avoiding them would be essentially impossible. And yet here we are, alone, quiet, sending radio signals into the dark and hearing nothing back. This is what scientists call the Fermi Paradox. But the von Neumann problem is sharper than the Fermi Paradox. The Fermi Paradox simply asks, where is everybody? Von Neumann's version of the question asks something more pointed. It asks, where are the machines? Because biological civilizations have limits. They need food and water and breathable air. They die. They have wars. They might choose not to travel. But machines do not have those limits. A von Neumann probe does not get tired. It does not run out of food. It does not decide it would rather stay home. It just replicates and moves forward, forever, until it has covered everything there is to cover. So the absence of von Neumann probes is actually more disturbing than the absence of alien radio signals. Radio signals fade. They spread out across space and get weaker with distance. You could easily miss a radio signal from a civilization 1,000 light-years away. But you cannot easily miss a self-replicating machine that has had millions of years to multiply and spread. That is not something that fades. That is something that compounds. The silence is not just strange. The silence, given von Neumann's mathematics, is almost impossible to explain. Scientists and philosophers have spent decades trying to explain it. And the explanations they have come up with fall into a few broad categories. None of them are comfortable. All of them have serious problems. But they are worth going through one by one, because each one tells us something important about where we might actually be. The first explanation is the simplest and the most crushing. Maybe we are alone. Maybe the emergence of intelligent life is so extraordinarily unlikely, not just unlikely, but almost infinitely improbable, that in a galaxy of hundreds of billions of stars, it has only happened once. Here. Us. The fact that we exist does not prove that life is common. It only proves that life is possible. Those are very different things. We could be the one winning lottery ticket in a universe that has been running the lottery for nearly 14 billion years. This explanation is called the rare Earth hypothesis, and it has more support among serious scientists than most people realize. The conditions that allowed life to develop on Earth are not just unusual, they are stacked. The right kind of star, the right distance from that star, a large moon to stabilize the planet's tilt, a giant outer planet like Jupiter to absorb incoming asteroids, a magnetic field to protect the surface, plate tectonics to recycle nutrients. The list goes on. Each condition on its own might be fairly common, but all of them together, in the right combination, at the right time, the odds start to look very different. If intelligent life is genuinely that rare, then the silence makes sense. There is no one out there to build von Neumann probes. There never was. But most people find this answer deeply unsatisfying. Not because it is wrong, it might be right, but because it places us at the center of everything in a way that feels uncomfortably like wishful thinking. It is the scientific version of believing you are the main character. And history has not been kind to that kind of thinking, so scientists looked for other explanations. The second major explanation is darker. It is called the Great Filter. The idea is this. Somewhere along the path from simple chemistry to spacefaring civilization, there is a step that almost nothing survives. A filter. A wall. Something that kills off the vast majority of civilizations before they ever get the chance to spread beyond their home planet. If that filter exists, and if most civilizations hit it and do not make it through, then the galaxy could be full of dead starts. Planets where life began, intelligence emerged, technology developed. And then something went wrong. Something terminal. The terrifying question is where that filter sits on the timeline. If the Great Filter is behind us, if the hard step was something that already happened in our past, like the emergence of the first living cell, or the jump from single-celled life to complex multicellular organisms, then we got lucky. We made it through. The path ahead might be open. There may be no wall in front of us. But if the Great Filter is ahead of us, if the thing that kills civilizations is something that happens at our level of development or just beyond it, then the fact that we have not found anyone else is not reassuring at all. It means almost everyone who reached this point did not survive it. And we are about to find out why. Nuclear weapons are one candidate. A civilization that develops the ability to destroy itself before it develops the wisdom not to is a civilization that hits its own wall. Climate collapse is another. The misuse of biological technology is another. Artificial intelligence, developed faster than the ability to control it, is another. None of these are far-fetched. All of them are things we are actively dealing with right now. The Great Filter hypothesis does not require exotic explanations. It might just require us to look at our own news headlines. The third explanation is stranger and in some ways harder to dismiss. What if the civilizations are out there, but they are choosing not to contact us? What if there is some kind of agreement, a rule, a policy, a shared understanding among advanced civilizations that you do not reach out to planets that have not yet reached a certain level of development? This is sometimes called the zoo hypothesis. The idea that we are being watched, deliberately, from a distance, and that the silence is not natural. It is managed. This sounds like science fiction. But think about it from the other direction. If we discovered a planet with primitive life, bacteria, maybe some simple animals, what would we do? Would we land and immediately start making contact? Or would we observe from a distance, careful not to interfere, not to contaminate, not to disturb the natural development of what we found? We already have something like this thinking built into our own approach to exploring other worlds. We sterilize our spacecraft to avoid contaminating other planets. We have protocols for this. A more advanced civilization might have far more sophisticated versions of the same instinct. The problem with the zoo hypothesis is that it requires every single civilization in the galaxy to agree on this policy and stick to it, forever, with zero exceptions. All it takes is one civilization that does not follow the rules, one that is curious enough, or reckless enough, or simply different enough, to break the silence. The fact that none of them apparently have is itself very hard to explain. The fourth explanation is the one that does not get talked about enough in mainstream science. What if the probes are already here and we just do not recognize them? Von Neumann probes, by definition, would be built to last. They would be built to operate autonomously for millions of years. After that much time, they might not look like anything we would recognize as technology. They might look like rocks. They might have settled into stable orbits and gone quiet, waiting for some signal or some threshold to be crossed before they activate. They might be so small that we have never had the instruments to detect them. Or they might operate on principles so far beyond our current understanding that we would not know what we were looking at, even if we found one. There is a specific hypothesis, proposed seriously by scientists, not conspiracy theorists, that a von Neumann probe might have parked itself in a gravitationally stable point near Earth and gone dormant, waiting. These gravitationally stable points are called Lagrange points, and we have actually looked at some of them, though not comprehensively, and not with the specific intention of finding something that has been deliberately designed to be hard to detect. In 2017, an object called Oumuamua passed through our solar system. It was the first confirmed interstellar object ever observed, meaning it came from outside our solar system entirely. And it behaved strangely. Its shape was bizarre by any natural standard. It accelerated in a way that could not be fully explained by solar radiation pressure alone, and the mainstream scientific community concluded it was probably a natural object, a fragment of some distant planet or comet. But a Harvard astrophysicist named Avi Loeb published a serious, peer-reviewed argument that it could have been artificial. Not that it definitely was, but that the possibility could not be ruled out by the data. The scientific community largely rejected his conclusion, but they did not fully refute his data. And the debate itself revealed something important. We do not actually have a comprehensive systematic program for searching our own solar system for objects that might be artificial. We are not looking carefully. We have not been looking carefully. And if you are not looking, you are not going to find anything, regardless of whether it is there or not. This is a problem that goes beyond Oumuamua. Our entire approach to the search for extraterrestrial intelligence has been focused almost entirely on radio signals from distant stars. That is a very narrow search strategy. It assumes that alien civilizations communicate the way we communicate, or at least the way we communicated in the mid-20th century, when this search strategy was first developed. It assumes that the signature of intelligence looks like a deliberate broadcast. But von Neumann probes would not broadcast. They would not need to. They would just work. Quietly. Persistently. In ways we might not be looking for at all. The fifth explanation is the one that challenges the deepest assumption of all. What if interstellar travel, at any meaningful scale, is simply not possible? What if the physics that von Neumann's thought experiment assumes, that you can send a probe to another star, that it can survive the journey, that it can operate in a completely alien environment, or that it can find and process raw materials on a world it has never been designed for? What if all of that turns out to be far harder in practice than it is in theory? This is a legitimate scientific concern. The distances between stars are almost incomprehensibly large, even at a significant fraction of the speed of light, which is itself far beyond anything we can currently achieve. The journey to the nearest star takes years. Cosmic radiation at those speeds would be brutal. The energy requirements are staggering. And the idea that a probe could land on a completely unknown asteroid or moon and successfully mine it for the exact materials it needs to replicate itself assumes a level of adaptability and robustness that goes far beyond anything we have ever built. Maybe von Neumann's mathematics is correct in principle, but the engineering is impossible in practice. Maybe every civilization that has ever existed has run into the same wall, that the universe is simply too big, and the distances are simply too vast for any physical object to bridge them in a useful time frame. Maybe the silence is not a mystery at all. Maybe it is just physics. But this explanation has its own problem. It requires every civilization, across billions of years, across hundreds of billions of stars, to hit the same engineering wall and never find a way through it. It requires that no civilization ever found a workaround, a shortcut, a method we have not yet imagined. Given the timescales involved, that is a very strong assumption. You are essentially betting that the most resourceful and intelligent beings to ever exist, given millions or billions of years to work on the problem, never solved it. History suggests that given enough time, intelligence finds a way through most walls. So where does that leave us? It leaves us in a deeply uncomfortable place. Von Neumann gave us a framework that is mathematically airtight. The logic is clean. The numbers work. If self-replicating machines are possible, and there is no known physical law that prevents them, and if any civilization existed long enough to build one, and given the age of the universe, the odds strongly favor that at least one did, then the galaxy should be full of them by now. The absence of any evidence of them is not a small anomaly. It is a screaming, galaxy-sized contradiction. And the resolutions to that contradiction are all, in their own way, devastating. If we are alone, that is devastating because it means the universe is almost incomprehensibly empty of the one thing that makes it interesting. If the great filter is behind us, that is a relief, but it still means intelligence is so rare as to be essentially a cosmic accident. If the great filter is ahead of us, that is perhaps the most frightening conclusion available to rational thought. That the arc of technological civilization bends, almost inevitably, toward extinction. If the probes are here and we are in a zoo, that raises questions about free will and observation and contact that we are nowhere near equipped to answer. And if the probes are here and we simply have not found them, then we are living inside a mystery that we may not have the tools to solve yet. None of these answers let you go back to thinking about the night sky the same way. There is one more thing worth saying before this ends. Von Neumann himself never framed this as a crisis. He was not a man given to alarm. He was precise, methodical, almost unnervingly calm. He laid out the logic of self-replicating machines the same way he laid out everything else, as a problem to be understood, not feared. He believed that intelligence, properly applied, could work through any problem it encountered. That was his fundamental conviction. But he also understood something that most people do not. He understood that the value of an unsolvable problem is not in the solution. It is in what the problem forces you to confront. A problem that has no comfortable answer forces you to examine every assumption you were relying on to stay comfortable. It forces you to look at things you have been avoiding. It forces you to be honest about what you actually know versus what you have been assuming. The von Neumann problem forces humanity to be honest about its place in the universe. Not the place we would prefer to have, not the place that makes the best story. The actual place. And the honest answer, right now, today, with everything we know, is that we do not know. We do not know if we are alone. We do not know what the silence means. We do not know if something is coming or watching or simply absent. We are a species that has been asking this question for thousands of years and has gotten, in return, nothing but more silence. What von Neumann added to that silence was mathematics. He turned a philosophical question into a technical one. He said, "Here is what the universe should look like if intelligent life is common and capable. Now explain to me why it does not look like that." And in doing so, he made the silence louder. He made it harder to dismiss. He made it into something that demands an answer rather than just inviting a guess. We have not found that answer yet, but the search for it is not idle curiosity. It is not a hobby for astronomers with too much time on their hands. It is arguably the most important investigation the human species has ever undertaken, because the answer, whatever it turns out to be, will tell us something fundamental about what we are, where we are going, and whether we are going to make it. The universe is old, the galaxy is vast, the mathematics is clear, and the silence continues. Von Neumann built the door. Nobody has walked through it yet, but it is there. And on the other side of it is either the most relieving truth imaginable or the most sobering one. The question is whether we are brave enough to keep knocking.